Yeah. All right.
Goggles over glasses.
So what we're going to end up doing today is I'm just going to kind of go through the liquid nitrogen. Mr. Klein is going to help us. He teaches chemistry and physics here at FHS. But if you read through the first question, okay, it says liquid nitrogen in a flask. Why does the liquid nitrogen boil? Okay, so now, obviously a lot of you probably know the answer to that. Some of you may not. So we're going to kind of just talk about that as a whole class, but I'm going to show you how this works first of all. Liquid nitrogen is honestly probably a lot more safer than dry ice because it typically does not occur on Earth unless you're finding it in a lab or some sort of hospital setting. You're not going to find liquid nitrogen because nitrogen is typically in what state? A gas, right? So what we do is we reduce the volume and we also reduce the temperature at the same time because the gas in here that's nitrogen is going to be what's used. So they actually it goes through a huge process to make this. The problem though is that when liquid nitrogen hits something that's warm, and pretty much everything is warm compared to liquid nitrogen because liquid nitrogen is actually at negative 320 degrees Fahrenheit, I believe, right, at the top. And so if you think about everything that you know using the Fahrenheit scale, there's not a lot of things that are colder than that. So it's really hard to kind of keep liquid nitrogen into anything. So here I'm going to pour it into this container, and you can see what it looks like, and it's boiling. Now the cool thing is also is that it actually is, when we're looking at the liquid nitrogen, it doesn't have a lot of resistance. Its ability to change is has a very, very easy ability to change. And so when we look at this, I can kind of swirl this around and it moves incredibly fast. We call this something called viscosity, all right? Compared to water, water would have a hard time moving in this direction at this speed for that duration of time, but liquid nitrogen seems to do that. Now, notice that there's all this like fog kind of forming on the outside. What's going on? How is that forming? Yeah.
It's turning into a gas.
So the gases are coming up through here, and that's sort of right, but can we see nitrogen out here? No. No. So what is that white gas?
Vapor.
Okay. And when we're talking about vapors, we're talking about what? Certain vapors. What particular vapor are we talking about? So what else is in the air other than nitrogen, oxygen? What other things are in the air other than nitrogen, oxygen, or any other gases? Because a lot of gases we can't see, we can't smell. So what is all this smoke coming off? See, it's coming out of the bottom too. What is all that?
Condensation.
Okay, so good. What happens is the water hits this container. It's very, very cold, and it starts to freeze. And so what we see here is that freezing effect. And for example, in this case, what happens is that the cold air is being shot up through this little area right here, and we are seeing that the gases that are being produced is very, very cold, and it's actually producing what we call water vapor. Okay, so it's like that's going to be water that's kind of coming out. It's the water from the air that's shooting out of that little valve right there. And so it's so cold that the water around it is actually starting to change phases, and we can actually see it a little bit better. So a lot of that is going to be water vapor. Okay, that's the steam. All right. And the biggest reason for that is because you can't see gases, most gases I should say. You can't see oxygen, you can't see CO2, you can't see nitrogen. So when nitrogen goes from a liquid state to a gaseous state, we have problems there. We can't see it. So what is that? It's just the water vapor. All right? So going back to the questions, why does the liquid nitrogen boil? What would be a really good answer for that?
Because its boiling point is lower than the room temperature.
Yeah, good. Perfect. If you want to simplify that, you could say because everything around it is considerably warmer compared to the liquid nitrogen, and so everything's going to boil, cause the liquid nitrogen to seem like it's boiling, all right? It's kind of interesting to see like something boil, but not have any direct flame underneath of it. You know what I mean? Kind of interesting to see that. Okay, so the next one is what is the white cloud that's being produced? What did we say the white cloud was?
Water vapor.
Yeah, a form of water vapor. The water that's in the air right now, okay, and there is water in the air, okay? We call it, a lot of us consider this humidity, water in the air, okay? And so when there is water in the air, it will actually, you can see that steam because we actually cool it off. And has anyone ever seen this happen? For example, you're breathing outside, right? Exactly, or humidifier, perfect, good. So those are great examples of that. All right. Number 1C, when it's poured on the ground, what happens? Now, hopefully everyone in here has some sort of sole around their shoe in case the liquid nitrogen comes on the ground. But we're going to go ahead and pour this onto the ground. Don't touch it, okay? It's cold, but it's really cool, the appearance, what happens.
Whoa. It's like a haunted house.
Well, look at the little molecules that they're moving across the ground.
That was like a breeze on my feet.
You felt it, the coldness?
Oh, I feel
I like
the cold.
breeze.
What's that? Yeah. But that's the dry ice. Now, I have no problem pouring out the dry ice, just throwing it over my jacket over there, and that's okay. Last year, actually, I didn't have students move out like this, and there was a student that left their bag right underneath this area, and I'm like, all right, let's pour some liquid nitrogen out. And I started pouring the liquid nitrogen out, and the kid's like, you're just pouring it all over my floor. And I'm like, oh, hey, it's okay, it's not a problem. Their assignment was all wet, but it dried out really, really fast. Because it was a lot faster than water if you were ever poured into water. But really kind of a cool little situation there because the individual was all worried, and I was like, don't worry about it, it's not going to cause any problem. All right, so we should have number 1 completely done, all right? When it's poured on the ground, where does the liquid nitrogen go? That would be C. And what would you guys say for that?
It spreads out around it.
Okay, yep. So it spreads out, and it also goes into a gas phase. We call that what? It goes from a liquid to a gas. Think about when you boil water. It goes from a liquid to a gas. It does what? Evaporate. Yep. So we already evaporated. The liquid nitrogen is evaporated. Okay. So I'll have number 1 done. Number 2 is the balloon on liquid nitrogen. Okay, the balloon on liquid nitrogen. So here's a balloon, and we're going to put it in this container because it's a lot easier to see. Why is the balloon inflated? Talk to me about what the molecules are doing. Exactly, right? They're bouncing around, they're hitting the sides of the balloon, and the more that they keep pushing on the sides of the balloon stays inflated. Does that make sense? We can't fathom how fast these molecules are actually moving. We can't simulate that with a simulator, but they're moving really, really fast. So what did I tell you happens when you take this balloon and you put it in a very cold environment? It'll shrink, right? So a lot of you probably have never seen this before, so it's going to make it kind of spectacular and special. balloon doesn't like this very much, but I think it's awesome. So what happened to the balloon?
Freeze it.
Whoa.
So it's very, very, like basically it went down, I take it out, I put it back up on here.
Cool. I'm terrified it's gonna pop.
Pop! And we could do that again. All right? So tell me what's going on to the molecules in here. That's actually question 2A.
Freezing them. They're like not moving anymore. So.
Okay, so I like the fact that you say that they're freezing. When something's freezing, the molecules are no longer moving as fast. Prior to putting this balloon in the liquid nitrogen, is the same amount of molecules, air molecules in here, the same before as after I pull it out? What do you think? Are the molecules going to be the same amount? Thank you. Yeah, just grab one of those pieces of paper over there. It looks like the demonstration. Yep, that one. Actually, no. The other one. Yes. So again, okay, I take it out. Is the amount of molecules that are inside of the balloon before I put it in going to be the same as when it shrivels up?
Yeah.
Exactly. So where do those molecules go then? Good. Perfect. So I want you to mention something like that for question number 2A. Once I pour the liquid nitrogen over the balloon, why does the balloon shrivel up? The molecules are still the same amount, but they shrivel up into a smaller area. And Mr. Klein informed me a couple days ago that you can actually do the same thing. If you fill this up with pure oxygen, you can make liquid oxygen. And it's actually one thing that, I mean, like, I don't know where I would get pure pure oxygen, because only thing I can think of is people that may have, for example, lung diseases and they have to be on oxygen continuously. That's the only place I can think of where I could get pure oxygen.
Cutting torches.
Or cutting torches, that's a good one.
Different gases and torches.
Yeah, that's a good one. I never even thought about that. So, again, going back to this, why does it inflate? Number 2B, why does the balloon, when I take it out, inflate?
They spread back out.
Huh?
They spread back out.
And why are they spreading back out?
It's not cold.
Because they are collecting more thermal energy and heating up. Perfect, okay?
I like to think of the analogy as when you get cold, you just kind of huddle up and cuddle together. That's what the molecules in there are. They're just kind of sticking around together. And when it warms up, you spread out because it's just too warm to be near someone.
And then, does it actually inflate to its original size and volume? For the most part, yes. I mean, there's maybe like a small difference, but if, for example, I just want you to let you know that, like, over time, this balloon will get smaller because the gases will be able to leave through the balloon. There's little tiny pores in the balloon, and they can actually leave. A great example of this is if you don't air up your tires over a long period of time, your tires are eventually going to go flat. But most of you have probably witnessed when you have going into a winter months, your tires are inflated. They're good to go. Everything's good about them. But then you get into January, and what happens to your tires? Yep, they start deflating. So you want them to. You typically are supposed to air your tires up in the winter months, and then during the spring months, what do you think you're supposed to do?
Let some air out.
Let some air out. Exactly right. So you don't overinflate and overstretch that wall. And then if you do that, if you overinflate them, that actually puts a lot of tension on the tire, and it doesn't allow them to hold their air as easily. So, yep, perfect. Okay, so we're done with all of 2. All right, so now it's the liquid nitrogen in the flour. All right. So I have a funny story about these.
They look so pretty.
I know, right? They look amazing.